and I've got the big question of the hour now. How many watched the videos of what we missed last week on Wednesday? Anybody? Somehow I was afraid of that. Okay, so we'll pick up where we left off last Monday, if that's okay with y'all. So we'll go from current slide, and if my memory is right, well, this is the slide we said we were on, and it looks fairly similar. Oh, this is, let me back up. We did example 3. Ah, there we go. Bottom of the page. I had 2 marks on this page. Sorry about that. Here's where we left. First, any questions from all of your review of the things you did last week? Okay, on Wednesday. All right. If not, we're at the bottom of page 274 after example 3, which I think we did finish, right? Everybody? Were we there? Okay. Then, interesting thing. All before, we've always considered the x to be the independent variable. And, of course, the y is the dependent variable. So, and then a variable of integration, though, in a definite integral, the variable is sometimes called a dummy variable. So the independent variable, which sounds like the more important variable, is really a dummy, okay? It's a dummy variable because it can be replaced by any other variable without changing the value of the integral. Because if you're going from 0 to 3 of x plus 2 dx, that's the same as going from 0 to 3 of t plus 2 dt. It doesn't matter what you call this. In a definite integral, you're going to integrate it away, and it doesn't matter the name. They have the same value because it doesn't matter what letter you put there. Because of the definite integral, it's going to go away. Indefinite integral, yeah, you'd still have an x, you'd still have a t, so the answer would be the same, only the variables would be different. Here, the variable's going to disappear because you're going to plug in numbers for your limits. Okay? Anyone want to do that just for funsies? Y'all don't look very fun this morning, so let's just go on. We'll get to the next one. So let's deal with properties of definite integrals, top of page 275. Okay? The definition of definite integral of f on the interval a to b specifies that a be less than b. I mentioned that several times last week, I think. Okay? Now, however, it's convenient to extend the definition to cover cases when a is equal to b or a is greater than b. And I've yet to figure out what's convenient about it. You can do it, but I don't see that it's all that convenient. Geometrically, the next 2 definitions seem reasonable. For instance, it makes sense to define the area of a region with 0 width and finite height to be 0. Okay? If there's no width and finite height, 0 times 7, 14, 83, 4 million is still 0. So that's the first of these definitions. If f is defined at x equal a, so f has to be defined there. Now, if f is not defined there, if that's an index, this doesn't make any sense at all. But if it's defined at x equal a, then the integral from a to a, which is not going anywhere, okay, of f of x dx is just 0. That makes pretty good sense, doesn't it? Now, if f is integrable on a to b, meaning everywhere you can take an integration, you can integrate it, okay? No discontinuities in there and other things like that. Then the integral from b to a of f of x dx is exactly the opposite, meaning opposite in sign, negative of the integral from a to b, f of x dx, okay? Now here is the only thing that makes sort of reasonable sense to me, and this has its limitations too. Like before, you consider f the height. Oh, Frank's here. Good deal. I know you're in here. There you are. All right. Now, before I get too much further, did you do the video that covered last Wednesday stuff?
Was there?
You did?
No, sir.
Oh, you didn't. Okay. Well, that makes it unanimous. So we're just picking up where we left off at the end of last Monday. Okay. Now, this isn't a really good description of this, but it suits me okay. If F is sort of the height and B to A is the width, if you're taking a negative width, then you negate the area. Okay, so that is what, so if you reverse the sign, that, not that you can have a negative area or anything, but this isn't quite the same, but that just means if you're doing this minus that, and this one is this minus that, then that's the opposite of it, so you'll have to have the negative of that. Now, we don't outright go on and intend to do this, but there are times, and if we get to it, I think we will see it, when you do substitutions and things like this, a substitution may reverse the order of integration, so it's helpful to have that property. Okay, so let's evaluate each of these. What is the integral of antiderivative or integral of sine dx as x goes from pi to pi? 0, okay? You don't need to do an antiderivative or anything else. As soon as you see those are the same, stop, okay? This is the one, they did have it as a, not quite an example, but an illustration before. Now we are going to do it. What would that be? First say, what's the antiderivative of x plus 2? Antiderivative of x plus 2. Okay, now wait, let me... I forgot. I haven't told you how to do an antiderivative. We haven't done the fundamental property of calculus yet. So I was just starting to launch into this, and I remembered, nope, we haven't done that yet. Now, to do that, yuck, we've got to do the geometric thing. Remember that? Except, do y'all all know how to do this? To do it? To plug in? If not, it's a good time to learn it, okay? You do the antiderivative. What's the antiderivative of x? X squared over 2. Antiderivative of 2, 2x. Okay. Now, I shouldn't do this yet because we haven't done it yet, but I'm going to go on and do it. What you do is plug in x equals 3 down here and x equals 0 up here. After a while, you won't write the x equals, okay? But just for purposes. So start with the top one. When you plug in 0 there, what do you get? You get a 0, okay? When you plug in a 3, what do you get? Okay, but here, the bottom one you subtract, and this is the deal. Sorry about this. What do you get when you subtract x squared plus 2? When you plug a 3 in for that, what would that be? 9 halves, and you also subtract 6. 2 times 3 is 6. So this will be, like you said, that's 4.5, so that's negative 10.5, right? Now, what they wanted us to do, and this is indeed true, in fact, this is what I would have done, make that the opposite of 0 to 3, sorry, I'm doing my antiderivative already. No. Okay. X plus 2, and you get the same answers, x squared over 2 plus 2x, this time from 0 to 3, but you see you have a minus in front of it now because of the minus in front of the integral, and that gives you the same negative 10.5 minus 0. Okay, so that's what they get. They do minus 21 halves. And the reason they do that, they say, go back to example 3b, and that's exactly what we had there. So that's what they had us doing. I was going to have us go on and do the trapezoid, but if we had done this last week, we would have said, we just did that, and we got 21 halves, so this time it's minus 21 halves. So they were sort of breaking the, they were doing a little cheating of their own. Ah, here he is. I was beginning to think when the cat was away, the mouse was playing, huh? Okay, good to see you. So he'll be back sometime this week?
Oh, yeah, he's getting back tonight, actually.
Tonight, okay. All right, and you had to be here to tell him what he'd missed, right? Okay, okay, good deal. Okay, we just finished doing this, so we're going to see how they do it. The first one, because the sine function defined x equal pi, and the upper and lower limits of integration are equal, from the previous definition, that had to be 0. In other words, you're measuring some area under the sine curve, but with 0 width, okay? Finite height, 1, but at 0 width is 0, okay? If you think of that as areas. All right? The B part, that's the same given in 3b, except the upper and lower limits are interchanged, so it's the minus of that. So the integral from 3 to 0 of x plus 2 dx is the same as minus the integral from 0 to 3 of x plus 2 dx. And from last week, last Monday, when we did that, using the area of the trapezoid, we found that was 21 halves, and Fred decided to sneak in while I wasn't looking, but I caught you anyway, okay? Did you deal with the folks there yet, or are you going to do that now? Business office? Okay, yeah, just don't forget, because they didn't make any indication that was included. I wanted to make sure you knew it is included, so check with them. All right. So that's going to be exactly the opposite of the one we did last week, which was 21 halves last week, so it's minus 21 halves this week. Make sense? So you see, integration is not just dealing with areas. It's a good way to think of it, but it's not just area. How can you have an area that's negative? You can't, but you can certainly have integrals that are negative. Okay. Now, in this figure, 425, it's on the same page, which, by the way, that's page 275. This larger region can be divided into x equals c into two subregions, okay? And whose intersection is that line segment, that dotted line right there, which of course we know has 0 area. Because the line segment has 0 area, I just said that, it follows that the area of the larger region is equal to the sum of the areas of the two smaller regions. So this area plus that area is that area, okay? Now again, they're using the illustrations of areas. Integrals don't have to be areas, but this one, of course, is a good representation of it. This is the integral from a to b of f of x, there's your f of x, dx. And you can split that into these various little strips and approximate it, let the delta x's go to 0, and that gives you a dx. That's it. Well, because of that, you can break this as the integral from a to c, f of x dx, and then the integral from c to b, f of x dx. And remember, just because the letters are out of order, c is less than b, so that's still a legitimate integral. This leads to the additive interval property for integrals. If f is integrable on the 3 closed intervals determined by a, b, and c, then the integral from a to b, f of x dx, is the integral when they have this relationship. They really needed to say that a is less than b is less than c, okay? No, a is less than c is less than b, okay? If that relationship holds, then the integral from a to c of f of x dx plus integral from c to b of f of x dx is equal to the integral from a to b, because these two are the same values, so sure enough, that is equal to that. Now, I guess, let me think, if they were any other order, it probably would still work. Well, I don't want to say that. If A is less than C is less than B, that for certain works. Okay. We should have said that because they're referring to that figure. All right. Now, why would you do that? Okay? It's much easier to just integrate from A to B, isn't it? Well, what if maybe F was discontinuous here? Maybe it came down here, but then this one picked up and did that. Then, by judiciously placing that as your thing, you could do the area here plus the area there. And you could then take an integral of a function that had a finite number of discontinuities by judiciously placing the intermediate intervals in the right places. You could do that if you needed to. All right. Now, even if you don't have a discontinuity, if you have something that just makes it messy, okay? For instance, if you're trying to do the integral from -1 to 1 of absolute value of x dx, well, I don't know a rule for absolute value. There is no rule for absolute value. So what you do is write down what absolute value is. And this seems to have been the better way to approach this problem. This would be the integral from -1 to 1 of a piecewise defined function, which is minus x anytime x is less than 0, and positive x anytime x is greater than or equal to 0. Okay? Dx. Now that's a weird way of writing, but that's exactly what the absolute value of x is. That's the piecewise defined function. So let's split it into pieces. Let's do the first piece, the integral from -1 to 0, okay? And that would be the integral of minus x, okay? Dx, okay? Plus the integral from 0 to 1 of this one, x dx, okay? And that's exactly what they've got here, and that's how they got it. From taking the definition of your piecewise defined function, and absolute value of x is piecewise defined anytime you have minuses on one side and positives on the other, you have it's not a break in continuity, but it's a break in differentiability. If you remember that, at the point down there, it's not differentiable. And since you're going to be taking an antiderivative, it sort of helps to have something differentiable. So even though it's not discontinuous, you still have a break in differentiability. So do the break there and do that. Now, since we don't know how to do this yet, or aren't supposed to know how to do it yet, what you can do, and this is even easier, is graphing this, and it's going from -1 to 1, and this goes to 1 on either side here. So this is half of the square, right? 1 by 1 square, so that's 1/2, and this is another half of this, so this is equal to 1. So this will be a 1/2, and this will be another 1/2, doing it geometrically. And I really want to do it algebraically too, or calculusly too, but we're not going to do that yet. We'll get around to doing that later. Okay? But let's see how they do it, just for funsies. Okay? Area of a triangle, area of a triangle. That's exactly how they do it. Okay? They didn't draw the picture. Well, or did they? No, they didn't even bother drawing a picture, did they? It was bottom of page 275. But that's how they did it. And that's equal to 1. Fantastic. You learned something new today. 1/2 plus 1/2 is what? Go home and tell the folks this is what they're paying for. All right, that leads to theorem 4.7. If f and g are both integrable on a to b, and k is a constant, then the function kf and f of f plus or minus g, both of these are functions. They're both integral on a to b, and these are, I wish they went on and named them, these are your linearity theorem, you know, that the integral, this means that integration is a linear operation. The integral from a to b of k alpha of x dx. If k is just a constant, no dependency on any variable, or at least not on x, then you can pull it out of the integral and do the integral of f of x dx from a to b. Or if you're doing the integral of f plus or minus g of x, they're both integrable functions, remember, from a to b, then you can do the f first and then plus or minus the integral of g. Now, I'm sure there must be some time when it's advantageous to do that, but most of the time it's just as easy to go and integrate them like this. But you can do it. It's certainly a thing you can do if you need to. Notice that the property 2 of this can be extended to cover any number of functions. As long as they're integrable on that interval, then you can have plus or minus h, plus or minus this, and just every one of those represents another interval, if it's easier to do that way. All right, so here's example 6. Okay. Oh, they're giving us part. Okay. They say evaluate this integral here using each of the following values. They're just going to tell you off the top that this integral from 1 to 3 of x squared is going to be 26 thirds. The integral of from 1 to 3 of x is going to be 4, and the integral from 1 to 3 of dx is going to be 2. Now, we probably knew both of those last two already, but if you didn't, well, at least the last one. Okay. They're giving you this. Don't worry, I'm not going to give you this many of the times. Okay. So, what will this be? That would be minus, we're going to split it up, the plus and the minus. That will be minus the integral from 1 to 3 of x squared using the constant rule and the sum and difference rule dx, plus 4, pulling out the 4 out of the integral, of x dx minus 3 times the integral of dx. Okay, and both of these are from 1 to 3. Okay. Now you see the magic that happened here? We pulled the minus sign out, and that left you this, plus the integral, pull the 4 out, integral of x dx, and then pull the minus 3 out and do the integral from 1 to 3 of dx. And that's exactly what you got from up there. And we know this is 26 thirds. Magically, we know that. So this is minus 26 thirds plus 4 times 4, because this integral is 4, minus 3 times 2. All that's left is math. It's not even algebra. It's just math. Minus 26 thirds plus 16 minus 6. Well, which you rather go? Mixed numbers or fractions? I don't care. You tell me. Fractions? Okay. 16 thirds will be minus 26 thirds. 16 thirds is 48 thirds, if I'm thinking well. I think I am. Minus and 6 thirds will be 18 thirds. Right? Okay? So add your minuses together, and you get 39 thirds, and add your 48 thirds, and that will be minus, boy, it seems like I've done so. Oh, that's a 26. I can't read my writing. Okay, that's a 43 thirds. Okay. I was going to say that can't possibly be the answer. That's a 26. I was reading it as a 21. Okay, 26, 18, that's minus 34 thirds plus 48 thirds would be a 14 thirds. So let's see, if we did it with mixed numbers, this would have been negative 8 2/3, right? And negative 8 2/3 and negative 6 would be negative 14 thirds, and a positive 16, that would be 1 2/3. Oh, lose something here. 8. Negative. Boy, the old gray cells aren't working too well this morning. That's 44 thirds. Yeah, y'all, thanks for the help, everybody. Glad y'all are with me. 44 thirds plus 8 thirds. If I can get my pen back, it's a 44 thirds. Okay, so that's 4 thirds, which is 1 1/3, which I think is what I got before. Negative 8 2/3, negative 14 2/3, plus 16 would be 1 1/3. Got it. Finally. Okay. I'll be so glad when we're through this Mickey Mousing it and get to doing real calculus with it. That is coming, by the way. Oh, I forgot to ask you two when you came in. Did you do the YouTube video covering where we left off last time up till? No. Made it unanimous. Okay. That's why we're doing it now. All right. So let's move on. That was example 6. Here's, I think, let's watch how they did it. Hopefully they didn't do as many serious mistakes as I did. And they did string it out a little bit more. They first broke it into sums. So it's the integral from 1 to 3 of minus x squared dx plus the integral from 1 to 3 of 4x dx plus the integral from 1 to 3 of minus 3 dx, doing each of these parts separately. Then pulling out the constants, a negative here, a 4 there, and a negative 3 there, they did this, minus the integral of 1 to 3 of x squared, which we know, plus 4 times, pulling that out, the integral from 1 to 3 of x dx, which we know, minus 3 times the integral of dx, from 1 to 3 of dx, which we also know. And then plugging those in, you get negative 26 thirds plus 4 times 4 is 16, minus 6, which is 4 thirds, okay. Then they skipped right to the thing. Did everything else in gory detail, but then went right to the answer. They don't like doing math either. Okay. Now, any questions on that before we leave it? Okay. If f and g are continuous on some closed interval a to b, and f is always between 0 and g. So in other words, both f and g are never negative. They could be 0, but never negative, okay? And f is never greater than g. Could be equal, but never greater. And, of course, your x is between a and b, a being less than or equal to b. Then the following properties are true. First, the area of the region bounded by the graph of f and the x-axis, as long as f is positive, non-negative, let's put it that way, between a and b must be non-negative. Well, if f is non-negative, which this says it has to be, and a is less than b, so b minus a is non-negative, then f has to be The area under F is non-negative. Second, that area must be less than or equal to the area under G. In other words, if you integrate all three sides of this inequality, the area of 0 is 0, okay? The area of F has to be greater than or equal to 0 and less than or equal to the area under G. It's just that you can integrate all three and the relationship holds, okay? So integral from a to b of f of x dx is always less than or equal to g of integral from a to b of g of x, if f of x is always greater than or equal to f of x. And they're both always positive. All right. I guess they threw that in here because they hadn't really said it anywhere else. All right. So I think, oh, and here's those two properties generalized in this theorem. If f is integral and non-negative on the closed interval a to b, then 0 is less than, then when you integrate this, if f is integral, f is non-negative, okay, on a to b, then that means f is greater than or equal to 0 everywhere. Integrate both sides, that's 0, and that's less than or equal to that. If f and g are integrable on a closed interval a to b, and f is always less than or equal to g at every point x, for every x in the interval a to b, then the integral of f of x dx is always less than or equal to the integral of g of x dx. If both of them have to be positive, okay, and actually, since they did take that out, this is still true even if, let's see, can I say that? Yeah, it's just that you're no longer dealing with areas. You have negative areas, so that's fine. Ayana is here. By the way, I probably should have said this earlier. I sort of did, but didn't break to do it. But now I will. For those who did get to attend the honors and award ceremony last Thursday, several of our members were honored there. Congratulations to all of you. And a few of you who are out playing games were even mentioned. So congratulations to you too. Okay. I hope you won. All right. Good. All right. So this is preservation of inequality is what this is called when you're dealing with integrals. If your functions have a certain, I want to say Boolean relationship, but that's probably not quite the right word, then so does do the integrals of those functions. All right, and that ends 4.3. Homework exercises here would be number 3, that's both at Calc Chat and Calc View. Any of the odds 5 through 9, they're all at Calc Chat, 7's at Calc View. Number 11, which is at Calc Chat. Any of the odds 13 to 21, they're all at Calc Chat. 23, well, any of the odds 23 through 31, they're all at Calc Chat. 25's at Calc View. Any of the odds 33 to 39, they're all at Calc Chat. 37's at Calc View. Any of the odd, either 41 or 43, they're both at Calc Chat. Should be. And 45, it should be at Calc Chat as well. You can think about doing 47 if you'd like. It should be at Calc Chat, and 49. So I'll let you think about both of them. Or 51. Okay. Any one of those you can think about doing. Then there's exploring concepts. You can do 54 if you'd like. It should be at Calc Chat. And then either 55 or 57. You can explore doing those. Then you can do either 59 or 61. They should both be at Calc Chat. 63. Any of the odds 63 to 67 should be at Calc Chat. 69 is a Riemann sum. 71's a proof. You can think about doing 73 if you'd like. Finding some value, 75. Think about doing 77 and doing another Riemann sum at 79. Any questions? So let's get out of this and go to 4.4. Finally, we're here, where we've been anxiously awaiting the fundamental theorems of calculus. They say one, but then they give them two parts. So let's go to the slideshow from current slide. Chapter 4 is integration, and 4.4 is the fundamental theorem of calculus. We'll evaluate a definite integral using the fundamental theorem of calculus. I already hinted, and we did one problem with it. We're going to do plenty now. Understand and use the mean value theorem for integrals. We'll find an average value of a function over a closed interval. We'll understand and use the second fundamental theorem of calculus. Some books call them part 1 and part 2. This calls 2 fundamental theorems. So they should have had theorems. And we'll understand and use the net change theorem. Is there another? Nope. So let's do fundamental theorem of calculus. The first one. Okay. You have now been introduced to the 2 major branches of calculus, differential calculus, integral calculus. At this point, these 2 problems seem unrelated, but there is a very, very close connection. Well, we've already seen that. Integration is taking an antiderivative. Yeah, there's got to be a connection here. The connection was discovered independently by Isaac Newton and Gottfried Leibniz and stated as the fundamental theorem of calculus. And the really interesting thing about this, and I guess it could be that they were completely independently discovered. Taylor, right? All right. Is that they lived at the same time. And how in the world was it that we had been the entire existence of mankind? And yeah, people even back in Archimedes' time had been playing around with the concepts that were going to lead to this, but sure enough, they both approached it. Newton was approaching it from very much a physics viewpoint, from areas of arcs and ellipses and things like this, and accelerations and velocities and that type of thing. Leibniz was sort of more ethereal in his approach to it, and yet they lived at the same time and came up with it at the same time. It almost does seem pretty suspicious, but they seem to have done it. For a long time there was all these accusations of who copied who and who was plagiarizing whom and that kind of stuff, but it really does seem like even their approaches were from such different perspectives, and yet they came up with it at close to the same time. Newton, of course, claimed he had thought through it and written about it and done for years before Leibniz, but Leibniz, as soon as he discovered it, he published, okay, and that's where the rub came. Informally, the theorem states that differentiation and definite integration are inverse operations of, I would even contend indefinite integration too, but they'll say definite. In the same sense that division and multiplication are inverse operations of each other. The term operations take on a whole new meaning when you're talking about differentiation. Division, those are just algebraic operations. These are calculated operations, I guess you would say. To see how Newton and Leibniz might have anticipated that relationship, consider the approximation shown here. Okay? Now, there are times when I find these helpful, and sometimes I say, what are they getting at? Okay. Here, when you're doing differentiation, you can talk about the secant line and from a delta y over a delta x, and let the delta x get smaller and smaller and smaller, and of course the secant line will then creep down the curve until it becomes a tangent line. That is what you do with differentiation, okay? That, the slope then becomes a dy dx when the delta x goes to 0, okay? Now, That's differentiation. Definite integration, when you're talking about areas under a rectangle, if you just have one big delta x here, delta y times delta x, that's an approximation, but it's not a very good one, okay? Just like this wasn't a very good approximation of the slope of the tangent line, okay? But if you then sum up lots of little rectangles, so you're, and this is where they don't make this really clear at all. Delta y, delta x here, they just sort of lose the blue part here. Well, that's if you're letting your, I would have put a sum here and let the delta x's get very, very small, then you get this area here. So to go from a secant line to a tangent line as you creep down the curve, that makes sense because your delta x is getting smaller. This doesn't show how you get to this unless you do a summation of a bunch of delta x's, little strips there, and that gives you the area under the curve. Okay. But it still doesn't show, to me, nothing is intuitively obvious about how these are related to each other. Maybe there's some magical thing that I'm missing here, but yeah, this is how we did this, and this is how we did that, but that there's some relationship between the two of them is not intuitively obvious to me. Sure, well, they don't even show them being the same rectangles or the same curves. They reduce this one a little bit, but they do look like opposed to the same curves. And I guess that's supposed to do it for you. But the fact that as you let the delta x's get smaller, you get the answer you're looking for both ways. Best I can do with that. The slope of the tangent line was defined using the quotient delta x, y over delta x, slope of the secant line, letting the delta x get smaller and smaller and smaller. Similarly, the area of the region under the curve is defined using the product of delta y times delta x. And maybe this is what they're getting at. Just like division and multiplication are inverse operations, so are these. A little bit of a stretch, but maybe that's what they're saying. That's the area of a rectangle. So at least in the primitive approximation stage, the operations of differentiation and definite integration appear to have inverse relationship in the same sense as division and multiplication, or inverse operations. The fundamental theorem of calculus states that the limit processes used to define the derivative and definite integral preserve that inverse relationship. Okay? Now, this is what we've been waiting for. Okay? Fundamental theorem of calculus, at least the first one. If a function, little f, is continuous on a closed interval a to b, and capital F is the antiderivative of little f, just like we were using before when we were doing indefinite integration. Antiderivative of f on that same interval. Then, if you do this integration, integral from a to b of little f of x dx, do the antiderivative, capital F, evaluate it first at the upper limit, and then subtract from that at the lower limit. This is what I was doing for you earlier. I said, look, we haven't done it yet, but this is indeed what we do. Okay? And we don't have to do geometric. We don't have to remember those I-squareds, all those kinds of things. All we have to do is plug in the top, find the antiderivative, plug in the upper value, and subtract from that the evaluated lower value. It works. Every time. Okay? So the following guidelines can help you understand the fundamental theorem of calculus. Okay? Provided you can find the antiderivative of f. That's the big deal. Okay? Sometimes that's pretty obvious. Sometimes it's anything but. You now have a way to evaluate a definite integral without having to use a limit. Oh, shucks. We were just beginning to love our limits, weren't we? Okay? Or sums, the limit of a sum or geometric shapes or anything else, you can do it straightforward. When applying the fundamental theorem of calculus, the notation shown below is convenient, and this is what I was using. So the integral of f of x dx, just like we used to, take the antiderivative of your f, little f, that gives you capital F, evaluate it from, we usually say from A to B, but we always evaluate f of B minus f of A. The upper one minus the lower one. Okay? So, if we're doing this one, integral of from 1 to 3 of x cubed dx. First, what's the antiderivative of x cubed? Hurry up, my arm's getting tired. Huh? X to the 4th over 4. Evaluate that at 3. 3 to the 4th is, anyone know? Say again?
81.
81, okay? Minus, and then evaluate, 81 fourths, I'm sorry, 81 fourths. And then minus, when you evaluate it, 1 4th, and 81 fourths minus 1 4th is 80 fourths, which is, you've been watching, 20, okay. Sure enough, that's it. The antiderivative of this is x 4th over 4. Just go and do the antiderivative. Evaluate it from the lower to the upper, upper to lower, it doesn't matter how you say it, but be sure you plug in this one, 3 to the 4th over 4 minus 1 to the 4th over 4, and that's 81 fourths minus 1 4th is 20. Not necessary to include a constant of integration in the antiderivative. That's only for indefinite integrals, when you don't have the limits here. You always have to do it there. If you put one in here, that evaluates as f of b plus c minus f of a plus c minus c is 0. It comes out that way. Don't even bother with the constants of integration. If they're constants, they're going to subtract out anyway. So leave off the constant of integration when you have definite integration. Yay! All right, we always forgot to do it anyway, didn't we? So let's evaluate some. Let me get my pen set up. Whoa, I already had the pen. That's what I want. Okay. What's the antiderivative of x squared? Anybody? Oh, it's been a long time. X, say again?
X third over 3. X to the third over 3.
X cubed over 3? Is that what I heard? Okay. Minus, what's the antiderivative of 3? 3x. And evaluate that from 1 to 2. Plugging in the upper one first. And 2 cubed is, help me? 8 thirds. Minus 2 times 3 is? Not that hard. 6. Okay, then you subtract, so that'll make it a minus. 1 cubed is? 1 third. And minus a minus, which makes that a plus. 3 times 1 is 3. Now, warning, these little signs here are going to sneak out there and trip you up as often as they possibly can. So take your time, write them out, don't rush them, because here's a minus that was here, and when you do the lower one, this becomes a minus, and that becomes a plus. So however it takes you to do it, okay? If you need an extra step there, put it in. All right, so let's, 8 thirds minus 1 third will be 7 thirds minus 3, right? And that would be, what, 7 thirds minus 9 thirds, which is minus 2 thirds. Obviously not an area, right? Okay? Because it comes out negative, okay? Yes, negative 2 thirds. Any questions? So, just because we've always been thinking of them in terms of areas, don't have to do that anymore. In fact, if you think about this, if you graph this, that would be a parabola, but you move downward 3 units here, so you've got something below the x-axis. So that area is going to be negative, and sure enough it is. All right, how would you approach number B? I did too much talking on that one. You tell me how to approach number B. I'm going to do this even though I'll probably regret it. I'm going to pull out the 3. Then I'm going to write the integral from 1 to 4. What would you do next? Any of you have a hankering of taking the integral of a radical? Don't. Rewrite it as x to the 1/2. Okay? And then put your dx. That's the same thing. Okay? Now, what's the antiderivative of x to the 1/2? Okay, you're already dealing with the 3's. That was good to do. I pulled them out. I would say x to the 3/2, right? You increase that by 1, it'll come back. Yeah, okay. And then divide by 3/2, which is the same as multiplying by 2/3, which sure enough, the 3's are going to cancel out. And that leaves you from 1 to 4. Okay? So, I would pull the 2 completely out now and just do the evaluation here. Anyone know what, this one I will write this out. This will be 4 to the 3/2 minus 1 to the 3/2. Now, what in the world is 4 to the 3/2? What does the half tell you to do? Square root of 4, which is just 2, and cube it, and you get 8. Okay, so there'd be 2 times 8 minus, and what's square root of 1? 1, and 1 cubed is 1. So you have 14, right? Somewhere here. There we go. Yep. Make sense? All right, the one we've been waiting for, folks. What in the world is the antiderivative of secant squared? Oh, man. Anyone remember? Antiderivative of secant squared.
Is it tan squared times secant squared?
Okay, I think you're sort of going the other way. Not quite. Okay. You think, what function, when I take a derivative of it, do I get a secant squared? Does that help? Tangent, that's it. So therefore, the antiderivative of the secant squared would be tangent x. Now, I should have done a timeout first. Now, I'm going to back up. Pretend we didn't even do that. Do you remember anything bizarre about secant functions in general? It's also true about cosecants and tangents and cotangents. They are not continuous, except in certain intervals. What are the intervals for secant, where it is a continuous function? Second? Between half pi, negative half pi and pi halves, or pi halves and 3/2 pi. It's between the half pi's. They are continuous there. Therefore, it's very important that your limits not jump over one of those half pi's. If they do, hang it up jack. You can't do that, okay, because this has to be continuous there. 0 to pi-4, yes, no problem there. It's continuous. Defined at 0, it's defined at pi-4, and defined everywhere in between. So when you do deal with secants and tangents and cosecants and cotangents, be sure your limits make sense, and these do. So that is tangent x, and we're going to evaluate that from 0 to pi-4. And that means we do tangent of pi-4 minus the tangent of 0. Anyone happen to know what the tangent of pi-4 is? 1. Okay? And what is the tangent of 0? 0. So that answer is 1. All that to get 1. Okay. Make sense? Any questions before I erase? Is everybody still with the living? I hope so. Okay. So let's see how they do it. First one, integral of this. They take the antiderivative of x squared, which is x cubed over 3, minus the antiderivative of 3, which is 3x. Evaluate that from 1 to 2. 2 being first. That would be 2 cubed is 8/3, minus 2 times 3 is 6, so it's a minus 6. Then minus the same thing, put the minus sign. If this is how it's helpful you to do it this way, by all means. Don't let those signs screw you up here, because they will do it if they can. Okay? Minus, you plug in the 1, and that would be 1/3 minus 3. So there's a minus sign up front. Keep all that entity there, unless you do it the way I did, and then be sure you do it correctly. And then what I would do here, they're going to do 8/3 minus 1/3 is going to be 7/3, and then, oh, they just get the answer without showing you how they did it. But then this would be a minus 6 plus 3, so that would be a minus 3. So 7/3 minus 9/3 is a negative 2/3. All right. The B one, integral from 1 to 4 of this, and they did the same way. I'm surprised. They pulled the 3 on the outside, because you can, okay, and then change the square root of x to x is 1/3, x 1/2. As soon as you do that, then you know you can use the power rule to do the antiderivative, and that would be x to the 3/2, increase this exponent by 1, and divide by that exponent. But whenever it's a fractional exponent, I like to invert and multiply and just make it 2/3. Then the 3's cancel out, and you have a 2 in front. So that would be 2 times, now, I pulled the 2 all the way on the outside before I evaluated. You don't have to, you can do it this way. If you pull it outside, make sure you do it times the whole entity there. And 4 to the 3/2 is 8. 1 to the 3/2 is 1. So it would be 2 times, that would be 16 minus 2, which is 14. Which is the same thing we got, just I did it a slightly different way. Pulling the 2 out is 8 minus 1 is 7. 2 times 7 is 14. All right. And then the last one here, and again, they sort of glazed over it, but you have to always be thinking, is this defined here? And it is. 0 to pi-4 is perfectly fine. Secant squared, antiderivative of secant squared is tangent. Evaluate that from 0 to pi-4. Make sure that's doable. It is. And that would be 1 minus 0, which is 1. Good deal. Any questions? All right. Now, they're choosing to skip examples 2 and 3. No, I'm sorry. Yeah, 2 and 3 at least. We don't have to choose to do that, do we? So let's back up. We'll do example 2. Evaluate this. Oh, gag. Why did I say I'd do this? Okay. I don't like these. Evaluate the integral from 0 to 2. Oh, this isn't bad. Of absolute value 2x minus 1 dx. And if you had the same reaction I did, say, oh no, a piecewise defined function, yuck, do the integral in two different pieces. The good news is, this is a 0, okay? So you, oh, maybe it's not such good news, is it? Because when x is equal to 0, that is a negative value. So yeah, we still got to do piecewise defined function. Yuck. Okay. All right. Here's how technically I would say approach this problem. This may not be the way the book does, but this is what I say. What does this mean? The absolute value of 2x minus 1 is equal to 2x, the book usually does it reverse of this. I don't know if this book does, but most books do. I like to put the negative on top and the positive on the bottom. So that would be minus a 2x minus 1 anytime 2x minus 1 is less than 0. Okay? This is a weird way of putting it, but this is what this means. And it's 2x minus 1 anytime 2x minus 1 is greater than or equal to 0. Okay. I know that looks bizarre, but that's exactly what absolute value means. Okay? Now, let's deal with the conditions first. And they are going to go the same way. You're going to add 1 to both sides, right? Okay, and then this will give you 2x less than 1, and this will be 2x greater than or equal to 1. And then we'll divide both sides by 2. Okay, and this will be x less than 1/2 and x greater than or equal to 1/2. That's what we have to fiddle with. Okay? And then it has these two meanings for that. I just ran out of room. I wish I'd have had time. So basically what this means, we have two different integrals here. The first integral is going to be from, see, 0 is less than 1/2. So your first one's going to be 0 to 1/2, and then you'll use this top one, which will be a 1 minus 2x. Now notice how I just flipped that around because I don't like leading off with the minus sign. But see, I just took that one up there and reversed it and said 1 minus 2x. That's just my preference. You don't have to. You can do a minus 2x plus 1 if you want to. Just multiply through. That's the first integral. Okay? Plus, then the second integral will be from 1/2 to 2. Okay? Because there, x is always greater than 1/2. And then you'll be 2x minus 1. It'll come back. Okay. Now, as you can tell, I'm not a big fan of absolute value integrals. You know, they're easy to do, but you just have to think through the details, and that's what does it for you. Write down what that actually meant, you know, and it meant that that thing there is, it's the opposite of that when it's less than 0, when that whole thing is less than 0, and it is that when the whole thing is greater than 0. But you have to get those limits in place. And you see, it's not going from minus 1 to 0, it's going from 0 to 1/2. So, all right, let's do the integration. What is this? Antiderivative of 1. Oh, I left off my dx's here, didn't I? Sorry about that. All right. Antiderivative of 1. X. Antiderivative of minus 2x. minus x squared. That's evaluated from 0 to 1/2. Plus antiderivative of 2x, same x squared, minus antiderivative of 1, x, and that's evaluated from 1/2 to 2. Okay? So let's plug in the first. 1/2 minus, what is 1/2 squared? 1/4. I'll do the next one for you because I know y'all are tired. It's getting near the end of the class. When you plug a 0 in here, you get 0. So you don't have to worry about that one. Okay. I did it for you. Okay? Now let's do the second one. This one. Plus, and 2 squared is 4 minus 2. And then you're going to be subtracting a 1/2 squared. That would be 1/4. And then you've got a minus a minus, which is a plus 1/2. All right. Now, again, do whatever it takes for you to make sure you got the signs right. Okay? But if you string them out like this, not always, but in this case, it really doesn't do too badly. Kind of. Still is sort of bad. Here's a minus 1/4 and a minus 1/4. That's going to be a minus 1/2. So one of these 1/2s goes out with those. So let's just wipe out that, that, and that. And then 4 minus 2 is 2 plus a half, 2 1/2, or 5/2. I sure hope that's the answer. Yes, it is. Because I sure didn't want to go back and find my error somewhere up there. Anyone? Any questions? You see how that works? You can't just say, oh, this is going to be minus this from minus something other than 0. Oh, since this is that, yeah. No. You can't do that. You have to say, does this thing in here, when you plug in either one of these limits, give you a negative number? Yes, it does. This, when you plug in a 0, that would give you a negative 1. So no, you can't just say, oh, you don't have any negatives here, so you have to, no. You have to evaluate the whole thing, and that's why I went through that whole process there. And you see your actual limits are from x less than 1/2, that's going to be your minus part, and from 1/2 on up is going to be the positive part. Okay? Any questions? The book got it. Good for them. Now, I'm not sure they did it the same way I did. Yeah, they kind of did, but they kind of left off how they magically came up with the first step. Okay? I hope my showing you that helped there a little bit. Maybe. Any questions on example 2? Move on to 3. Okay. Example 3. Find the area of the region bounded by the graph. Y is equal to, how are we doing on time, by the way?
30 minutes.
How much? 30? Huh?
29 minutes.
Left to go. Okay, good. Okay. 30 would have been all right with me, but no, he got down to 29, didn't he? Okay. Okay. Find the area of the region bounded by the graph of y is equal to 2x squared minus 3x plus 2. Okay? Now, they were very nice to you in the book. Oh, between the area of the region bounded by that, the x-axis, and the vertical lines x equal 2, or x equals 0 to x equal 2. Is that right? Yeah. As shown in the figure, and they showed you the graph. Thank you very much for showing us the graph. Put it on the slide set and make it even easier. But they did the graph here, and I'll just duplicate it. it looks like it does something like this, okay? All right. Which is good news, because the whole function within these limits, in fact everywhere, seems to be positive, okay? So the x-axis is going to give us a good area. If this part had dipped down beneath here, you have problems, but it still works. And the calculus doesn't care about it dipping down there, but since they asked for the area, you do worry about the area, okay? But this, since it never drops down there, area makes sense. So we don't have to worry about what the value is up there anywhere else. We just do the math. Since this is dealing with an area, the area is all above the x-axis, we can just integrate it. So let's do that. It'll be the integral of 2x squared minus 3x plus 2 dx, and we'll do from the limits of 0, x equals 0 to x equals 2. Since we know that everywhere in there you're above the x-axis, so you're not going to have any cancellations. So that will give us that area there. Okay? So what's the antiderivative of 2x squared? 2x cubed, say again, over 3, minus, what's the antiderivative of 3x? 3x squared over 2, and the antiderivative of 2? 2x. We'll evaluate that from 0 to 2. Okay? Notice, isn't it nice not to have to deal with plus c's anymore? Okay. So, plug and chug, what do we get? X, or 2 cubed is 8 times 2 is 16 thirds, minus 2 squared is, times 3 is 12 over 2 would be 6, right? Plus 2 times 2 is 4. Now, I know y'all are tired, so I'll do the zeros for you. 0 plus 0 plus 0. All right, got them done. All right. So what does that yield? Well, if you get it in the third, well, let's first do 16 thirds minus 2. Getting that in the thirds would be 16 thirds minus how many thirds is 2? How many thirds are in 2? How many thirds are in 1? Ooh, you must be tired.
6 thirds.
That's 6 thirds, okay. And this will be 10 thirds. All right, hope they got, yes, they got it right. Good for them. All right, now there's several ways you can do that, but that's one of doing it. If I didn't have the graph, I couldn't honestly say that's going to be the area because I didn't know if that dip went below the x-axis or not. If it had have gone below the x-axis, then we would have had a positive value here, a negative area here, and a positive area here, and the answer would have been these two minus that. Okay? And I'm not sure that's what they're looking for. So when you have areas, you either have to draw the graph or convince yourself that it's not ever going to dip below there. So since they showed us the graph, we could just do the integration. And it worked. All right. Now we're ready for that old mean value theorem. All right. Mean value theorem of it for integrals. You saw that the area of a region under a curve is greater than the area under an inscribed rectangle and less than the area of the circumscribed rectangle. Well, if this is your curve here, and it looks like to me that may be your maximum value there. If you drew a circumscribed rectangle, that would be that. Inscribed rectangle would be the one down here, that's completely under the curve. Okay? So the area would be something in between. The mean value theorem for integrals states that somewhere in between the inscribed and circumscribed rectangles, the inscribed and the circumscribed rectangles, there is a rectangle whose area is precisely equal to the area of the region under the curve. And that makes sense geometrically, doesn't it? Okay? That if you had a rectangle up here and a rectangle down there, somewhere in between there's got to be a rectangle that's exactly the same. In other words, the area here that the curve, not included in the curve here, that the curve undershoots, and here this area that is not included in the rectangle but is under the curve, when these two areas are equal to each other, then this rectangle here has exactly the same area as the area under the curve. Okay? Now I don't want to mess with trying to make these two equal, but what we just saying is there is a rectangle there that makes it work. Okay? This is sort of one of those existence theorems, which is not necessarily how to find it, but just that it does exist. Okay. Now, that means there is some C in between A and B such that the f of C is equal to the, this height times that width is equal to the same area as the area under the curve. So the f of C times B minus A, which is the length of that, is equal to the integral f of x dx. This is what we're interested in. Okay? The problem is we don't know where the C is. Okay? That's why it's an existence theorem. We know there's one there, we just don't know where it is. And it's not particularly an easy one to find. Or is it? Okay? So here's the mean value theorem for integrals. If f is continuous on some closed interval a to b, now f being continuous, meaning no breaks, gaps anywhere in between, there's nothing going to infinity anywhere in there, okay? Then there exists some number c on the closed interval a to b, somewhere in between a and b, such that the integral from a to b of f of x dx is equal to f of c times b minus a. Now, again, just an existence, there has to be a c in there that works for f to be continuous. Now, if you need to find what that c is, you could divide both sides by b minus a, so it's b1 over b minus a, and then if this is an easy integral to do the integral, and that gives you f of c. Still doesn't tell you what c is, but if you know what f is, maybe you can figure out what the c is then. Okay? And yeah, okay. By the way, I'll leave that in my pocket. Okay. Why do I have that in my pocket? I think I remember. Okay. Now, in your text, where I did arm waving there and showed you the inscribed and circumscribed rectangle, they actually show you that in the text. I don't know why they didn't show you on the slides, but they didn't. They just showed you that one. But they don't do any examples, so let's move on then to average value of a function. Ha! That's what we were getting at, isn't it? The value f of c given in the mean value theorem for integrals is sometimes called the average of f on the interval from a to b. In other words, what's the mean value for the function on that interval? And that function could have been doing all sorts of weird things there. As long as it stayed above 0 and all that kind of stuff, then you can find what the average value was. So here's the definition for the average value of a function on an interval. If f is integrable, has to be integral, no gaps, infinities anywhere in there, on the closed interval from a to b, then the average value of f on that interval is this. 1 over b minus a, that was your length of the interval, length of that rectangle, times the height of the rectangle, is your f of c. That's what we're looking for. And that would be the 1 over b minus a times that interval. If this is an integrable function, you should be able to integrate it, and you'll get the average value that way. So that alpha c. We won't know what c is maybe, but we will know what alpha c is, which is the average value of that function on the integral. Now, in this figure, 432, and, oh yeah, this is up at the top of page 285, yeah. The area of the region under the graph of F is equal to the area of the region of the rectangle. Okay? So you see this F has several ups and downs in it, although it's still a pretty regular looking function up there. The average value undershoots the function here, the function overshoots it here, the function undershoots this here and overshoots it again there. So the average value is this f of c right here. We don't know what c is. It could have been this c, that c, or that c, but it's this value right here, okay, on the y-axis, okay? And that's what we're led to believe. Okay. Now, there are times I wish some of you were out there saying, why do we ever need to know this? But y'all don't seem to care. Well, no, I'm not saying that, did I? Okay. But what if you had, say, in your business, your market, doing a lot of fluctuation, and you really wanted to know what can I count on just sort of an average over some interval? This would give it to you then. Okay? Of course, that kind of thing may be a very difficult thing to integrate. But if you could do some type of numerical integration or something like that to give it to you, that would be a useful thing to know. Because you do have cycles, you know, but I want to know what it's going to be for the year, okay, or quarter, or whatever your interval. To see why the average value of the f is defined in this way, partition the interval from A to B into n subintervals of equal width, and that we've seen that before. Your delta x is your b minus a over n. If ci is any point on the ith subinterval, then the arithmetic average, or the mean, as in mean value there, of the function values at the c sub i's is y, I guess A for average, 1 over n times your alpha c1 plus alpha c2 plus all the way up to alpha cn. The average of all your alpha of ci's. Okay. By writing the sum using the summation notation, which is one of my favorite things to do, then multiplying and dividing by b minus a, you can write the average as okay. This average was the summation of all those divided by n, because you had n subintervals. And here they multiplied and divided by b minus a, taking the denominator one out, leaving the integral one in the interval. You can, there's no reason not to. And they drew this in. Well, then this becomes 1 over b minus a on the outside. Your summation, alpha c times delta x. That's what delta x, remember? B minus a over n. And then let the n go to infinity. Same length is there. And this becomes your integral. And that becomes the dx. Yeah, that gets you right back where we were before. Finally, taking the limit as n approaches infinity produces the average value of f on the interval a to b, given the definition above. In this figure, notice that the area of the region under the graph of f is equal to the area of the region of the rectangle whose height uses that average value. Okay. So the area under here is equal to the area under the rectangle. So the average value under the rectangle over this interval is the same as the height of that average value under the function is the same as the height of the rectangle. So both of them go from BA. Have we beat that dead horse enough? So let's do one. Find the average value of f of x equal 3x squared minus 2x on the interval from 1 to 4. So what's that average value going to be? The book, I don't think, uses this. I'm going to use it just because it's easier than writing average value, okay? Let's just call it, if it's okay. I can't get my pen back. There we go. Let's call it average value of f of x, like that. You know, just, I made up that notation. It's not in the book anywhere. Just the average f of x. What would that be? From what we just did? Started with 1 over something. What was that? B minus A. In this case, that would be? Second? 4 minus 1. Perfect. Okay. Times what? What's the rest of it? Trying to wake people up here. Okay. What's the rest of it? The integral from what? 1 to 4 of what? 3x squared minus 2x dx. Okay, that doesn't look like that's going to be too hard to do. What's 4 minus 1? Easy part. 3, 1/3. Oh, well, I don't need that. Let's just go on and do the antiderivative. What's the antiderivative of 3x squared? Second? X cubed minus x squared, evaluated from 1 to 4. Okay, so this will be a 1/3 times, okay, 4 cubed is, anybody? 64 minus 4 squared, 16, minus 1 cubed, not that hard, 1, minus a minus, which is a plus, 1 squared, which is 1. All right, these two I'll deal with, okay? And this will give you 1/3 of, what's that, 48? And I think that's right around 16, isn't it? Let's see what they got. Yes. Okay. Does that make sense? So the average value of that function looks to be about 16. Now this one they do. Can I go on and erase it and show how they did it? Okay. Whoops. All right. They started off with the average value being 1 over b minus a times the integral of f of x dx from a to b. And we know what those are. The b minus a is 1 over 4 minus 1. Integral from 1 to 4. And that's your function. And that gives you 1/3 times x cubed minus x squared from 1 to 4, which is 1/3 of 64 minus 16 minus 1, which is 0. So that'd be 48/3, which of course is 16. Now, the average value is 16. That's this thing here. That doesn't let you know what C gave you that. But if you wanted to try to do that, you could just then set that equal to 16, so that's what it's expected to be, and solve that quadratic equation. You're probably going to come up with something very irrational, okay? But if you really cared to do that, you could. All right. Usually all we're interested in is the average value of the function, 16. Any questions on that? All right, they seem to be skipping example 5. So let's go back and we'll do example 5. How are we doing on time?
7 minutes.
How much?
7.
7. Let's see if we can get it done. Maybe not. Okay, goodness gracious. At different altitudes in the Earth's atmosphere, sound travels at different speeds. The speed of sound, s of x, in meters per second, can be modeled by this piecewise defined function. Now, I told you they were my favorites, right? Yeah. Okay. Near the surface of the Earth, it's a function that is decreasing with altitude because the air molecules are getting further and further apart. Okay, but then it goes almost constant from at certain higher altitudes, and I can't begin to tell you why. Then it goes to an increasing function, slightly increasing at a higher altitude. My guess is temperature has something involved here, because as you go up, temperature also decreases. And then it goes up to a steeper increase for a little ways, and then starts to decline again. And that's why you have really strange looking function here. What is the average speed of sound over the interval from 0 to 80? That will take a little while to do, I think. So let's start with that next time, okay? And sorry about this, going to cheat you out of some of your tuition dollars, but we'll begin there. We got decent progress here, but this is a long section. Homework exercises here, you can do either 5 or 7. They're both at calcchat.com. You can do any of the odds 9 through 35. They're all at CalcChat. 19's at CalcView. Do either 37 or 39. They're both at CalcChat. 37's at CalcView. Then do any of the odds 41 to 45. They're all at CalcChat. 43's at CalcView. You can do any of the odds 47 to 51. They're all at CalcChat. 47's at CalcView. I think you can do 53 to 57. They're all at CalcChat. Thank you. 53's at CalcView. And we'll hold off the applied problems until we do that next one. Okay? There are not many more to do. All right. Any questions? All right. Have I cheated you out of some of your tuition dollars now? 4 minutes of it. Oh, no. Forgive me. I didn't know what I was doing. Okay. So, I did, but we just couldn't do that next problem. And you got out of Wednesday class anyway? What is wrong with me? Okay. Don't go into that. Okay, we don't have time. Okay. No, last Wednesday. We don't miss this Wednesday. We'll be here Wednesday. Okay, I'm sorry. I shouldn't have said that, should I? Okay. For that while there, Jake, I thought you were wearing a kilt, you know. All right, got it. Okay. I was hoping it wasn't. That would have been a lousy view from up here. Okay. Good deal.
All right, so I need to go down to the business office and ask them about it.
Okay. I would do it on the Birmingham campus, not on this one.
Okay.
They won't know what you're talking about here, I don't think. They may, but the business office on Birmingham is the one that, or you're over there, so aren't you? Yeah. Just go by there anytime and just find out what you need to do and how, you know, what procedures they want you to follow to get credit for that.
Okay.
But basically, you got $500 in the bank, the Lawson Bank, not your bank. Okay.
Yeah. Thank you.
All righty, good deal. Where did he go?
He went to the Philippines.
Philippines. Oh, nice. Which area?
To what?
Do you know which island?
I I know it's like 2 hours out of Manila. So,
Okay, so it's probably still on Leyte, I think is that island.
I'm not sure.
Is it where they had the really bad typhoon damage several years ago, or?
I don't think so. He's at like a preaching school or something, so it's not like
Oh, I see. Okay.
repairing work. It's more mission work minded stuff. So,
Yeah. Okay.
but yeah, he's on his way back right now. So.
Yeah. We have several friends who are from Philippines. They're U.S. citizens.
Mm-hmm.
In fact, we know the kids of one family really well. One guy lived with us for a little while one summer, but let me turn this off. But we're